Hey, Fidelity. What's it cost to invest with the Fidelity app?
Start with as little as $1 with no account fees or trade commissions on U.S. stocks and ETFs.
That's music to my ears.
I can only talk.
Investing involves risk, including risk of loss. Zero account fees apply to retail brokerage accounts only. Sell order assessment fee not included. A limited number of ETFs are subject to a transaction-based service fee of $100. See full list at fidelity.com/commissions. Fidelity Brokerage Services, LLC, member NYSE, SIPC.
This episode is brought to you by Abercrombie. There's nothing better than the perfect jean and going out top combo, or an outfit that perfectly matches your plans. Abercrombie's relaxed jean goes with every occasion. Date nights with something lace, or daytime with a cozy sweater. And their barrel jean will surprise you. It's the trend that will become a staple in your wardrobe. Abercrombie denim comes in tons of rises, fits, and washes. Find your perfect pair online or in store. There are only a handful of known venomous lizards in the world. The Gila monster, found primarily in the American Southwest and Mexico, is one of them. Gastroenterologist Jean-Pierre Raufman analyzed animal venoms from various species, including the Gila monster. Raufman eventually discovered some intriguing molecules in the lizard's venom, a discovery he declined to patent. Other scientists took interest in the Gila monster, and eventually, those molecules became the foundation for GLP-1 drugs like Ozempic and Mounjaro. These drugs are best known for their help treating diabetes and obesity, but recent studies have raised hopes that they could address chronic kidney disease, reduce the risk of heart problems, and even cognitive issues and addictions to opioids. As David Deming recently wrote for The Atlantic, you can imagine a member of Congress in the 1980s denouncing the NIH's wasteful spending on useless studies of Gila monster venom. Today, we're talking about another, unrelated line of research that defies even my attempts to find clear, practical applications for modern-day humans. My name's Jerusalem Demsis. I'm a staff writer at The Atlantic, and this is Good on Paper, a policy show that questions what we really know about popular narratives. My guest today is Johannes Krause. He's a researcher with a PhD in genetics working at the Max Planck Institute for Evolutionary Anthropology. When early modern humans came out of Africa, at some point they interbred with Neanderthals. The evidence of those unions are in the genes of most humans alive today. A paper Krause recently co-authored with several other scientists helps pinpoint when this happened. Figuring out this prehistoric mystery is one step towards understanding why Homo sapiens are the only form of human left standing. Johannes, welcome to the show.
Yeah, very glad to be here, Jerusalem.
So in 2022, the Nobel Prize went to your colleague, and I hope I'm saying his name correctly, Svante Pääbo, for determining that Neanderthals mated with prehistoric humans. In an interview, he said, quote, "The last 40,000 years is quite unique in human history in that we are the only form of humans around." If right now you and I could travel back before 40,000 years ago and take a sort of census of human Homo genus species, like what would we find in different parts of the world?
So if we would travel back to, let's say, 100,000 years ago, we would find at least 3 different forms of humans, and we can debate whether we call them species. We are kind of careful just calling them forms, because species is a concept from biology, which has definitions, and there's many different definitions what makes a species. There's at least 25 concepts what makes a species. And for some groups, they work. For some, they don't. So we're kind of careful. That's why we call them forms. If you pay attention, we are also calling them only Neanderthals. Some of those archaic humans, other forms of humans that existed, and not Homo neanderthalensis, which would be this nice Latin term that has been introduced in the 18th century, which again comes with a certain species concept. So we're trying to be a little bit careful and neutral and just call them forms of humans. So Neanderthals were one of them, which is probably the most famous one that most people have heard about. Then, of course, it's us, modern humans. But then there were also other groups, like one that we discovered a few years ago that lived in Asia, the so-called Denisovans. They were named based on a cave that the bones were discovered in, where we got the first genome. But there were also other types of humans that have been discovered based on fossil evidence. So, for example, there was a group of humans that was called Homo floresiensis that lived in Flores, which is an island in Indonesia, probably until about 50,000 years ago when the first humans came there. There was also a group called Homo luzonensis, which was living in the northern part of the Philippines on the island of Luzon. That's kind of where the name is also coming from. So those are at least 5 different groups then, including us. But there's also some people that suggested there's something called Homo mabayensis, Homo daliensis, Homo erectus, maybe still present in some parts of Southeast Asia. So there was a whole bunch, at least half a dozen, maybe even more type of human forms that lived at that time, 100,000 years ago. And then 50,000 years ago, we emerge on the scene, we come out of Africa, and we largely replace most of them for whatever kind of mystical reason, kind of one of the kind of, basically big questions we have in evolutionary anthropology. Why are we the winners, basically, of that type of competition? And what do we have, which, like all the other groups, did not have?
What sorts of things distinguish these different types of forms of humans from one another? I know there's probably a lot, but, we have an image of a Neanderthal in our heads, but, early Homo sapiens also kind of looked a bit different than we look right now as well. So what kind of made us different from them and other types of humans?
So as geneticists, we can quantify the amount of differences, which is just counting the number of base pairs in the genome that are different between those, say, Neanderthals and kind of modern day people, which is not a lot. So this is about 0.1% of the genome. So 99.9%, they are identical in their genome to the people that live today, or kind of to modern humans that lived maybe even 50,000 years ago. So they share a common ancestor 500,000 years ago, Neanderthals and us. So at that time, we were one population, and then we started to kind of get different and diverge from each other. Over this time period of maybe 500,000 years, they also got morphological differences. So I think if we would meet them today, we would probably recognize they look a bit funny. They had pretty big eyebrows. They had a bit of a protruding nose. They were a bit more stocky than we are today. If they would be sitting on the New York subway, some people have argued maybe you wouldn't even kind of recognize them if they were wearing a hat and maybe kind of just have some clothes. And there's a lot of diversity in the world today of people that are a bit taller and a bit shorter and a bit more stocky. So in a way, it might even be kind of something that you might not recognize. But if you really pay attention, then they would look a bit different. Some people even say, there are people with similar features, individual features, that are still living today, because there's a lot of diversity in the world today. So you might have the individual characters that are found in Neanderthals in people today, but not in combination, basically in one person like it was back then. But they were quite similar to us, right? I mean, we would have recognized them as people. We would say they're humans. That's also when we talk about them. They're humans, right? They're not modern humans. They're not us, but they're humans. So they're quite similar. And again, we're 99.9% identical in our DNA to them. So they're probably not different. And they probably had some sort of language. Maybe if we would have tried hard, we could have also kind of communicated with them over time. But then at the same time, they must be different enough that there's a reason that they are gone and we're still there. So they got extinct. So there must be something that we have that they did not have. Otherwise, I think all those other groups of humans would have not gotten extinct. And that's kind of part of the motivation why we're so interested in them, trying to understand what is different in us, because that kind of then also comes then close to this question, what makes humans humans? What is so special about people today? What's so special about humans in general? Why are we the dominant mammal on the planet? And maybe those archaic humans can actually help us to understand, because they obviously did not have what we have today, because otherwise they would be the dominant mammal on the planet. And then what basically happened between them and us in this kind of short time period. We're talking about 500,000 years between a common ancestor with them and us today, which sounds like a lot, 500,000 years. A lot of people would say, well, that's a lot of time. But in evolutionary time, it's a very short time period.
So I want to turn to the study that you co-authored, and I absolutely love the origin story of this, because I think it underscores just how random discoveries can be. Can you tell us about how your new project came about?
Yeah, they all started in 2020 when one of my colleagues, Hélène Roger, who's a professor at Los Angeles, she's a paleoanthropologist, so she specialized in identifying little pieces of bone and kind of knowing whether those bones are human bones or whether those bones are animal bones. She was supposed to do a sabbatical, so spend a certain amount of time with us at our institute in Leipzig in Germany. And she came, but then she was supposed to look at some bones from a site that we had studied, which was in Czech Republic, where there was a lot of bones. The border was closed, so she couldn't go to Czech Republic. So we were like, okay, what to do? I mean, we're sitting with her here, she can't go anywhere. So I'm calling some of my colleagues from the neighboring cities if they have some boxes of bones that she could maybe look at from the past. And then one of my colleagues, Harald Meller from Halle, kind of closest city to our city here, was like, we have this 120 boxes from a site in Thuringia in central Germany that were excavated in the 1930s from a site that's called Ranis. And it's like below a castle. It used to be a cave that collapsed thousands of years ago. And it was excavated in the 1930s, and they had to stop because World War II started. And then they basically put all the boxes somewhere in the basement, and no one really looked at those boxes for like 100 years. And then, we're like, okay, sure. Helen was very happy to have something to do. So we just got all the boxes here to the Institute, and she spent 3 weeks on looking into the kind of boxes. These were tiny little bone fragments that were excavated from the basically Pleistocene, old layers from the Ice Age thousands of years ago. Mostly those were animal bones, but she found about 120 bones that she thought could be human. And there was about 28 that she said they are from a very old layer, because they were from boxes that were kind of labeled from the lowest layer of the cave. And they said that would be really cool because based on the archaeology that is associated to that old layers, they should be very old, very early modern humans, potentially. So we said, okay, let's analyze them. And we were not sure if they are modern humans, if they're Neanderthals, so kind of what kind of human could they be. And we sequenced the DNA, and yeah, to our surprise, we first of all found they were not Neanderthals, but they were actually modern humans. And what was amazing was that we also dated them. So we radiocarbon dated them to determine how old those bones were. And they were 45,000 years old. And that were then, based at that point in kind of radiocarbon dating, that we had the oldest human bones, modern human bones, so Homo sapiens bones, that we had available. And one of them even was the best preserved bone from the Pleistocene, so from the entire Ice Age. It had a lot of human DNA, so enough to do a very high quality genome. And then we did a whole genome analysis, and we found very old people from 45,000 years ago from the site in Thuringia that we had genomic DNA that we could study. Turned out one was a mother and a daughter. And we also found that some of them were related, 4th, 5th degree to each other. And what was even more amazing was that we had published just the year before already a genome from a very old individual, from a female individual, from a site in Czech Republic that's called Slatý kůň, which means in translation the golden horse. That's kind of the name of the mountain above the cave where it was discovered in the 1950s. Unfortunately, that could not be radiocarbon dated, but based on the genetic analysis, we could already say this was a very old person, because not in terms of age, but like how old that person kind of lived in the past. And it turned out that this individual was related to our individuals from Thuringia, from Germany, which is 300 kilometers away from each other, which was an amazing surprise. I mean, what's the chance that you look at some Ice Age people 45,000 years ago and you find the great-grand kind of cousin of that one person and the other person? Yeah. There's like, we have 10 genomes and, they happen to be related, which is really incredible.
It's like putting your DNA into one of those databases now and like finding a relative who lives next door.
Exactly. What's the chance, right? Or someone that you went to school with or something like that. It's very unlikely, but here we go. We had this like very close relationship. And we had complete genomes, and those genomes were really, really interesting to analyze because they also turned out to have still very long chunks of Neanderthal DNA. I mentioned it before. We could already show about 15 years ago, we sequenced the Neanderthal genome at the time, and we also sequenced the genome of the Denisovan, so of this other type of human that we then discovered. And when we looked at those genomes of those archaic people, we actually saw that all people outside Africa carry Neanderthal DNA today, and people in Southeast Asia carry the DNA of Denisovan. So there was some gene flow between those other forms of humans and modern humans.
So the first thing I want to jump in on is one of the big contributions of this paper, which is that we learned that there'd been this admixture between Neanderthals and Homo sapiens. But you're finding that this is happening much later than we had previously believed, and that there's this overlap of about 5,000 years when both human forms are coexisting. So what is important about learning all of that?
So we actually found that instead of, some people said it happened 50 to 60,000 years ago, it happened only about 47,000 years ago. And how did we find that? We found in our old genomes from Germany and Czech Republic that they carried very long chunks of Neanderthal DNA in those basically people's genomes. They had the same admixture event that everyone outside Africa carries today. So people in Europe have that, people in Asia have that. So they are part of the population outside Africa. But they had very long chunks, because over time the chunks become shorter. So because when you have basically two people recombining, so mother and father's DNA recombining, then the chunks get shorter and shorter over time. But they had very long chunks, which told us when actually the admixture happened, because it's like ticking off a clock. So long chunks become shorter and shorter through time. So if you have longer chunks, you can actually calculate when did the admixture happen. And we dated that to about 47,000 years ago. So about 50 to 80 generations before our individuals lived, they had admixed with Neanderthals. And now this is the admixture that is common to all people outside Africa. So we were for the first time able to say this happened 47,000 years ago. Before it was very indirect using genomes of today, and there was kind of lots of, uncertainty when it happened. And why is this important? It's important because there's hundreds, maybe even thousands of archaeological findings outside Africa that are attributed to modern humans, where people say this was made by modern humans. This was a modern human skull. This was a modern human tooth. This is like evidence of modern human presence outside Africa that are older than 50,000 years. So there's a lot of evidence for modern humans being present outside Africa before 50,000 years. But now we are saying that Neanderthals and modern humans only admixed 47,000 years ago, and everyone outside Africa has the Neanderthal DNA. So it's basically not possible that modern humans, at least how we know modern humans today, Europeans, Asians, Australian, Aboriginals, that it has to be then a different type of modern human, because all the modern humans today go back to a common ancestor that left Africa or kind of intermixed with Neanderthals only about 47,000 years ago. So everything that's older than 47,000 years ago has to be made by someone else. Or if it's a bone, it has to be someone else. And that's very important, because there has been really a whole lot of different studies published in high prestigious journals over the last few years for evidence of modern humans being present in Papua New Guinea 60,000 years ago, modern humans being present in Australia 60,000 years ago, modern humans being present in Vietnam 70,000 years ago, modern humans being present in China 100,000 years ago, 80,000 years ago, 70,000 years ago. And basically all of that is then not us. It's basically not the people that we know today outside Africa, because all of the people today outside Africa are from that common ancestor population that we were now able to date to 47,000 years ago. And that's quite important. So this is basically now dating, if you want, the out of Africa event, because that is then really the last point, that all people outside Africa were a common population, because we all share the admixture with Neanderthals that we could now date. So therefore, it's really important for human evolution to understand when that happened, because it gives us a common ancestor of all the people outside Africa.
And I want to make sure that listeners fully understand why you're distinguishing outside of Africa versus what's going on there. Can you expand on that?
So humans evolved, so modern humans, Homo sapiens, we evolved in Africa. So of course, our entire, lineage evolved in Africa. So the first kind of upright walking early hominins evolved probably 7 million years ago. And then about 2 million years ago, the first hominins left Africa. So Homo erectus left Africa, came to Europe, Asia, evolved into different types of Homo erectus. So there were the different types of humans. I call them humans, so hominins outside Africa. And that then included also Neanderthals, Denisovans, the different forms that we talked about. But then 50,000 years ago, we have the emergence of Homo sapiens, modern humans. So we leave Africa about 50,000 years ago, go outside Africa. And this was something that, of course, is a major event in human evolution. So something that basically gave rise to the human diversity that we have on the planet today. Part of that, of course, is the people that left Africa is not, everyone leaving Africa. It's just part of the genetic diversity. It's just a part of that population. So people even calculated it's only about probably between 5,000 to 10,000 people that left Africa.
Wow.
So there is more genetic diversity that's left behind in Africa, which is also reflected today. And just looking at the genetic diversity, there is more genetic diversity in Africa than outside Africa. So there is basically larger genetic diversity present. So if you compare the two genomes of two people from somewhere in Africa, you have an average about 6 to 7 million differences in the genome. Whereas if you do that for people outside Africa, you have 4 to 5 million differences in the genome. So there is basically more genetic diversity, which is part of that story because just part of that population left. And then when people come outside Africa, about 50 to 47,000 years ago, as we now know, they meet Neanderthals because they're there. They're outside Africa. They're probably somewhere in the Near East. They're probably somewhere in the Levant, so modern-day Israel or Lebanon or Jordania. And there they meet Neanderthals. They mix with Neanderthals. And from there, they expand basically into Europe, Asia, Australia, later on into the Americas. And they take this Neanderthal mixture with them. And that is a really big event that we know about now for 15 years. But we didn't know when it happened. And now we do know when it happened.
Mm-hmm. One unexpected finding in your study that you flagged for us earlier is the familial relationships that you're finding between individuals who are pretty far apart. There's one that I remember that, 230 kilometers or roughly 140 miles apart. You also find that there's a pretty small populations, and you're estimating these early populations as numbering only in the hundreds. So is this, first of all, how are you doing that? How are you figuring out what the population size is? And given that it's a pretty small population, is it surprising to find familial relationships among the fragments that you're finding today?
So it is not completely surprising that we find closer relatives with a small population. So of course, if you go into a rural region somewhere in the world and you kind of sample people genetically, then it's a higher chance that they are closely related than if you take that in New York City where there are millions of people living. It's basically a result also of the small population that we find so many relatives. How we do that, how we can actually measure that, how we look at relatedness is how you do it today, right? How companies are doing it. You send the DNA to they just compare the genetic profiles and see how much is identical, how much is different. And from that, you can measure how much, relatedness you see between two individuals. But what you can also do is to calculate, for example, population size. You don't compare the genome of one person to the genome to another person, but you actually compare the genome that you get from the mother and the father within a person, because you have actually two genomes, right? You not have just one genome, you have two. So you have 2 copies of chromosome 1, 2 copies of chromosome 2, 2 copies of chromosome 3, and so forth. So if you compare those two to each other, if you have a very large population, you expect that on almost every part of the chromosome, there is differences between mother and father. But if it's a small population, there happens to be by chance regions in the chromosome that come from a common ancestor quite recently. Because in a small population, you don't have much choice with whom you can have children with. And therefore, it's often the chance that you have children with someone who's actually not too far related from you. And that basically causes regions in the genome that are identical, where both chromosomes are identical. They come from a common ancestor. And this happens in small population, doesn't happen in large populations. So you can directly calculate basically what that means for the population size. And then we came to a calculation of about 100 to 300 individuals. So that's quite small because we're talking about a region that stretches from Britain, from the British Isles, which were at that time connected to Europe, and Poland. So it's a large region. It's like thousands of kilometers, only a few hundred people. Imagine that, right? Today we have, 1 billion people living in Europe. And at that time, it was maybe just a few hundred people living in Europe, which is really insane. Yeah. But then, of course, if you then happen to just find some of them, there's a good chance, if you find them by chance, that they are actually related because there were just 100 of them. It's like an extended family, basically. So if it's from the roughly same time period, then there's a good chance you'll find relatives, and that's exactly what we found. So we have basically 2 lines of evidence. First, the finding that we have relatives is kind of like expected if it's a small population, but also within the genomes of those people, we see that there were not a lot of people living at that time.
So given that there was this interbreeding happening between different hominins that you're finding in your research with Neanderthals, do you expect to find the same sorts of things with other types of hominins mixing in other parts of the world?
We have actually seen that. So we have found already 15 years ago when we sequenced the first genome of the Denisovan, this other type of human, which, jumped out of a box. It was like a super big surprise that we found in the lab a new form of human, right? If you think about that, when you do an excavation, you dig somewhere, you find a skeleton, a fossil, you're like, wow, amazing, we found a new type of human. But imagine that happening in the lab, right? I mean, I was the lucky person to discover it some years ago, and I was basically working in the lab. I looked at DNA sequences and looked at them on the computer and were like, wow, this is not Neanderthal. This is not one of human. That's something else. That's a new form of human. It's like incredible, right? And if we then, when we then sequence the genome of this new form of human, we also found that it's distinct to Neanderthals, it's distinct to modern humans, but it's actually more a sister group of Neanderthals, a bit closer to Neanderthals than it would be to modern humans. It's separated from Neanderthals about 300,000 years ago, but there are also some populations of modern humans today that carry some of that DNA, some ancestry from those Denisovans. And that is actually groups in Papua New Guinea in the highlands, so kind of like indigenous groups from Papua New Guinea, and also indigenous groups from Australia, so Aboriginal groups. They carry about 5% of their genome from this Denisovan group. And there's also some group in the northern part of the Philippines that has about 7% from those Denisovans. In fact, colleagues of mine have shown that there were at least 5 admixture events between Denisovans and modern human groups in different parts of Asia. So people in China and in Japan, for example, have different ancestry from Denisovans than the people on Luzon in the Philippines, and yet different type of Denisovan ancestry in Papua New Guinea and Australia. So they interacted multiple times. That's different to the Neanderthals. For the Neanderthals, we have one main event that is shared with all people outside Africa. But then we also have some local events where we have local people, for example, some individuals that were found in Romania, some people that were found in Bulgaria that lived 42,000 years ago, that lived 40,000 years ago. They had additional Neanderthal ancestry, so they had also admixed with additional groups. But they actually went extinct. They did not leave descendants. They did not basically give that DNA to people that live today. So therefore, today, all the people outside Africa only carry that one pulse of Neanderthal admixture that's basically shared with all the people outside Africa. But in East Asia, Southeast Asia, it's different for Denisovan DNA. So people from China or from Japan, for example, they have different Denisovan DNA than people living in Papua New Guinea or Australia. So there have been multiple events that are still present in the diversity of people living in those parts of the world today.
After the break, the ancient human genomes we'll never get to learn from.
This episode is brought to you by Progressive Insurance. Do you ever find yourself playing the budgeting game? Well, with the Name Your Price tool from Progressive, you can find options that fit your budget and potentially lower your bills. Try it at Progressive.com. Progressive Casualty Insurance Company and Affiliates. Price and coverage match limited by state law. Not available in all states.
The PC gave us computing power at home, the internet connected us, and mobile let us do it pretty much anywhere. Now generative AI lets us communicate with technology in our own language using our own senses. But figuring it all out when you're living through it is a totally different story. Welcome to Leading the Shift, a new podcast from Microsoft Azure. I'm your host, Susan Ettlinger. In each episode, leaders will share what they're learning to help you navigate all this change with confidence. Please join us. Listen and subscribe wherever you get your podcasts.
One thing I want to ask you kind of broadly about this research is about selection issues. Obviously, you need some level of preserved remains in order to do this sort of analysis. Most of these are found in very cold regions of the world, or things that can be fossilized and maintain their integrity, their structural integrity to some extent. Are you worried about how that might bias findings about this time period in history?
Absolutely. That is a strong bias. So in fact, we have a very hard time to find ancient human genomes from, say, equatorial regions, so places that are really warm in average temperature, people that are moist. They don't preserve DNA so well, like, for example, northern latitudes, because it's just too warm. The preservation is not good enough. We cannot go back to 50 or 100,000-year-old humans from Africa, which is unfortunate because there's as we said earlier, there's more genetic diversity. This is where humans evolved. That's where the really interesting stuff is happening. But that's actually where we don't have a lot of ancient DNA. We cannot really go back. I mean, there's some genomes. There's one actually from Ethiopia, which is about 5,000 years old. There's some, again, from Morocco. There's some from Malawi that are some even older than 10,000 years. So there is some ancient DNA maybe going back to the last 10, 15,000 years in Africa, but we cannot go back 50, 100, or maybe even more time ago. Whereas, for example, in Europe, the oldest human genome that has been analyzed so far by my colleagues here at the Institute is more 100,000 years old. So almost 500,000 years old, from a site in Spain, in Cima de los Huesos, which are some early Neanderthals, turns out, genetically, which was also very exciting to find, those early Neanderthals there, because it means that Neanderthals are at least 400,000 years old, which is also something that wasn't actually clear. So they're already on the Neanderthal lineage after they have diverged from Denisovans and from modern humans.
One big question that you raised at the top for us is this large mystery of why it is that Homo sapiens sort of won. And there's this general sense that I think we're taught when, in K-12 here, when learning about this time period in history, which is just that Homo sapiens were just better. For some reason, we were just a superior form of human, and we're able to kind of outperform and outlast all of these other forms of hominins. Can you tell me what the kind of prevailing wisdom is about why this happened?
There's a whole bunch of different hypotheses, and I kind of summarize some of them in a book that we just published, actually just a couple of weeks ago in English. It's called Hubris, where we kind of talk about the history of humankind, so the rise and fall of humankind, also with the kind of challenges that we have in the future, and kind of looking into the past. So the kind of big hypothesis we're talking there about is what makes us special, what do we have, what they did not have. And I mean, there's much speculation in that direction. So what we can see is that modern humans are extremely expansive in their nature. We are expanding very fast. We basically don't tolerate sometimes borders, to a degree where it's almost suicidal. If you think about going on a little raft into the ocean to discover an island 3,000 kilometers away in the middle of the ocean, who would ever do that? What the hell? What kind of drives people to go on some of those kind of crazy kind of adventures to discover kind of new land? I mean, even sitting in a rocket that shoots you to the moon. It's who would, why would someone do that? But, we are doing those things. We are adventurous in some ways. Our population is highly culturally diverse, and we're adapting surprisingly fast to different environments. We are living in all ecosystems you can imagine on this planet, from high altitudes to deserts to living on the ocean or living in the Arctics, which also no other mammal has like we have it, because we are culturally, we have a high plasticity, so we can really adapt super fast, which is also something that we don't really see to that extent with other kind of earlier human forms. And our population has been growing also surprisingly fast through time. So we have a lot of children that largely kind of comes then out of later time periods when we start with food production, so with agriculture and pastoralism. Then we basically produce food in large amounts, and then the population becomes, billions of people like we have today, which is a process that happens later after we came out of Africa. But it's part of the success story also, and also shows, and this is something where basically we conclude also in this recent book, that it should have a biological basis, what I'm now talking about, that agriculture and this kind of complex way of food production actually emerges in parallel in at least 5 different places in the world, starting about 5 to 10,000 years ago. So there must be something that modern humans had that kind of basically allowed us to develop this complex way of life, food production, domestication of plants and animals, that happens independently so many times. It didn't happen in the 100,000s of years before, even when climate was similar and stable. But about 10,000 years ago, there is something that basically is there in the kind of genetic makeup of the people that came out of Africa 50,000 years ago, that we seem to have all in common, that allows us to develop this complex way of life, which I don't think was there hundreds thousands of years ago. So that's really something that is unique, which kind of tells me that there must be a biological basis to that something evolved in Africa more than 50,000 years ago that allowed us to expand out of Africa to be in very short time basically replacing all other forms of humans. I mean, we're talking about 5,000 years, and all those earlier forms, Neanderthals, Denisovans, Homo floresiensis, Homo luzonensis, like all those groups were extinct, and we're the only ones left behind. And then, we come up with this incredible kind of way of living and complex culture. We settle all the kind of distant places, like the tiniest islands in the Pacific, in that kind of short time period of about 50,000 years, the entire planet. There needs to be a biological basis to that. I cannot imagine that this is just pure coincidence. But we can't point it now to one gene. We can't really say it's this gene, it's that gene. Maybe it's a kind of number of different genetic changes that happen. If we compare the genome of a Neanderthal to the genome of a modern human today, it's a surprising kind of similarity, as we said, 99.9%. But even if you just look at the specific differences, like how many genes are fixed different between Neanderthals and modern humans, there's less than 100 genes that are different between a Neanderthal and a modern human. But somewhere there, I think, and maybe a combination of several of them, hides exactly that type of mystery, what we have and they don't. But that's kind of what we're still kind of after, right? So even if we now have a Neanderthal genome and some of those other earlier genomes, we haven't really found yet exactly kind of the recipe, basically, what makes us so special. But I think we're getting much closer to that than we were 10 years ago, before we had those genomes of those archaic humans.
I know this is an area of research where just learning and understanding on its own terms is important, but I think that there are also some really interesting implications for modern day humans. I came across this study that found that a major genetic risk factor for severe COVID-19 was inherited from Neanderthals. Can you explain how that was found?
So this was my colleague, Svante Pebo, here at the Institute. He found that together with another colleague, Hugo Seeberg, from the Karolinska Institute in Stockholm. And what they made use of was a large kind of study and effort from another group from Finland, Helsinki, called FinGen. They collected patients' genomes from COVID-19 and kind of looked at severe cases and looked at their genetic factors that cause a stronger, basically, response or higher risk of actually having severe COVID compared to others. And they did find regions in different parts of the genome that gave a higher risk. And interestingly, the kind of region on chromosome 3 that has the highest risk to actually have a severe form of COVID and have a 3 times higher risk to actually die of it, was then found by Svante and his colleague Hugo here to come from Neanderthal. So basically, they just kind of made use of someone else kind of finding all those regions, and they looked like, could that be from Neanderthals? And it turns out to be from Neanderthals. It's somehow a bit of a fun fact to some degree, because it's not really so, okay, now we know it's from Neanderthals. Does it help us to cure COVID or kind of, to do something about the disease? It does not. But it does tell us then, of course, that this is something that actually came into the human population about, 45,000 years or 47,000 years ago, when modern humans and Neanderthals had mixed. It's not found in Africa. It's found outside Africa only because it came from Neanderthals when they had mixed. It's in high frequency in Southern Asia. It's in higher frequency in Europe. So it kind of points out a bit more the history of this interesting region and what kind of story might be behind it. Probably has something to do with some other diseases, which are not coronaviruses, but probably some other diseases that have caused this variant to be, for example, in high frequency in South Asia. So my colleagues are now studying it and trying to understand the exact mechanisms that are actually behind this more severe form of corona. And there are many other such examples where we have found that Neanderthals passed on some of the genes, some of their genes to us, which were actually good for adapting to certain environments. So, for example, immunity genes that help us to tackle some of the pathogens present probably in Europe at the time when they came here. There's also some genes, like a gene that people have in East Asia today that allows them to live in high altitudes. So, for example, Tibetans, like the Sherpa, which is this famous group of people living in Tibet today, they almost all of them carry a gene that came from Denisovans into the gene pool of East Asians, whereas the frequency in an average person from Eastern Asia is only about 0.1% of that gene. Sherpa have it to 100%. They all have it. So it was very advantageous to have that gene. And it came from Denisovans. And we do know now even that Denisovans lived in high altitudes, because in some cave in China, they found a bone that is from a Denisovan. We know that now genetically as well as based on the morphology. And that was found at 3,200 meters altitude. So they actually lived already for a long time in high altitudes, were probably over time adapted to live in that high altitude. And that helped basically the people like the Sherpa today to live in Tibet, which is quite useful. It's a bit more kind of a complex mechanism how this is actually kind of what it's actually doing. It's actually switching off the natural adaptation that all of us have when we go to high altitudes. Then your body starts to adapt to the kind of low oxygen levels. And basically those Sherpas switch that mechanism off, so it's not working anymore. But for living in kind of high altitudes for a long time, it's actually what you need. And that's an interesting example of something that we actually inherited from those archaics and gave us something that kind of made midlife for people better.
I feel like I want some more context on how different this can really lead humans, modern day humans, to be, because there's tons of mixture that's happened between the populations of, Europe and Asia, the Middle East, Africa, the Americas. There's tons of intermarrying and children that have been had. Is it just that there's such a short time period where that's been happening, where you still see like serious differences in the genetic codes of people in Tibet versus, Central Europe, like you said?
Yeah, so this is indeed the case. So like populations in some parts of the world have admixed more, in some parts of the world they have admixed less. Like the genetic differences between European populations are half as strong now than they were 10,000 years ago, because over the last 10,000 years, humans in Europe merged basically with like different parts. There was a whole group of people coming with agriculture from Anatolia about 7,000 years ago. There was another group coming from Eastern Europe. But then there are other parts of the world where populations have been more stable, like Inuit, for example, in, say, Northern America. They have been, pretty, unadmixed in the last 4,000 years. But even there was some mixture and there was some replacement with some other groups. And this is, in a way, if we wouldn't have modern medicine and technology, the environment still has a very strong selection on people. So one good example that I always tell my students is Australia. Australia today has by far the biggest rate of skin cancer in the world. Why is that? Because they largely come from Great Britain and Ireland. That's where most of that kind of population descends from. They moved to almost the equator. They moved to an environment that they're actually not adapted to. They come from Northern Europe, basically to, equatorial regions where the sun is very, very intense. They should have dark skin, like the Aboriginal population in Australia that has dark skin. They don't have skin cancer because they are adapted to living in this kind of latitudes on the equator, whereas the kind of Northern Europeans are not. It's not so much a problem today because you have, sun blocker, you have, all kind of medical treatments. So it's not a strong selection pressure anymore. But if you would give it natural kind of like 1,000 years or 2,000 years, basically, all Australians would look like Aborigines, right? Because their skin would just adapt over time to living on the equator. And that's kind of a natural tendency that happens, in fact, everywhere in the world. So you have, for example, Native Americans, for example, also. So Native Americans in North America and far in South America, they have lighter skin than the ones living in Bolivia or Ecuador living on the equator because they had to adapt. They actually came with lighter skin to the Americas, and then they kind of started to live in high altitudes as well as on the equator and got darker skin. So this is also a natural kind of tendency to adapt to living in equatorial regions. And there are, of course, many other such examples. This could be, the environment, like sun exposure. But it can also be diet, right? So in Europe, for example, there is this lactase persistence, which a lot of people have. So a lot of people in Europe can drink 2 liters of milk, which the majority of people in the world cannot do. But, 5,000 years ago, people started, with a lot of milk probably consumption. So probably 2,000 years ago peaking. And that caused, a variant to emerge that gave people the ability to drink a lot of milk in adulthood, which mammals usually don't have because no mother want to give basically breastfeed the offspring for the rest of their life. They want to get rid of that. So what Mother Nature did in kind of evolution was to switch the gene off that allows us to digest milk, which is the lactase gene. So normal people, that switches off, which is good. That happens with your cat, that happens with your dog, that happens with, any mammal out there. But then for humans, they started to drink a lot of milk because they had cows, so they kind of used the cow milk. But then it was, bad if you have that gene switched off because you get all kind of problems. But then, people basically kind of had a mutation that allowed them to drink a lot of milk, which was extra proteins, and then they adapted, and that's kind of adaptation now to the food, but not to the environment, but basically the kind of environment that we have created. So this is also something that is basically also part of that story. The local adaptation is something that, of course, different environments and also different types of foods are introducing, right?
So I've really pushed to try to figure out a practical application for modern day humans in this debate and in the research strain that you've been pushing on. And I was reflecting about why I was trying so hard to find that, and it probably has to do with the larger debate that's happening in the U.S. right now about the value of research that does not have an obvious direct material benefit to people. And we've talked a little bit about how it can help us understand genetic risk factors and understand the way that we can metabolize different foods. And you've walked us through that. But I largely categorize the research you're doing as interested in uncovering the truth about who we are and how humanity came to be, divorced from immediate practical considerations. How do you make the case to people about the value of this type of research?
So I'm working in the Max Planck Society, and we do basic research. So we are not driven by what can be turned into a product, what's applicable to, some sort of new, whatever, medical treatment, or what is something that will really, benefit humanity directly as some sort of, new discovery that will result in a new form of energy or a new form of, medical treatment or so. But we're really driven by, finding out new stuff, kind of basic research, trying to understand, in our case, where humans came from. What's their kind of evolutionary course? How did they adapt it? What makes humans humans? How are we different to other mammals? How are we different to other types of humans? Which is largely driven by curiosity and will not result directly in products that you could, easily kind of sell to your mother and say, look, I did this research and now we have a new vacuum cleaner or something like that, right? This is, maybe what a physicist can do or a kind of mechanic can do, but I cannot do. But then a lot of people are interested in ancestry. A lot of people are interested in history. A lot of people are interested in evolution and trying to understand how things evolve. And in my case, I'm also doing a lot of work. About half of my work is actually not on the evolution of people, but on the evolution of pathogens. So where did, some of the most infamous pathogens in the world came from: plague, leprosy, syphilis, tuberculosis, and so forth. And there I could even kind of, come up with this being relevant, because we try to understand, where pathogens emerge, how they change, what's the evolution trajectory, what's the mutation rate. So I do have also some examples where I could say that could be, relevant also for medical research and infectious disease biology. But in terms of human evolution, I think it is largely curiosity driven. And I think this is also what our society, the Max Planck Society, stands for, that we really kind of, we want to, create more basic research and try to understand, various kind of things that should be researched and should be understood. And I think that's an incredible luxury to have, I should also say, especially in these times that we're living today, where a lot of people question, why should we do research, right? Why should we spend money on that? Well, we need to save money for something else, either for defense or for, certain products or certain luxury goods, or just, even for food or for health, for a lot of people that are maybe marginalized in certain parts of the world. But you can also never know what your discoveries, your basic kind of science and kind of insights might actually generate in the future.
So, what you were saying about what drives you to do basic research really kind of reminded me to the same exact thing you said earlier about what may have made Homo sapiens special, this kind of desire to explore and research and find new things, even if there's not a very clear, obvious reason to do it. Like, why strike out to go see if that island is habitable? Why look to see who your ancestors are? I mean, these are questions that, maybe other mammals wouldn't investigate, but it maybe is what makes us different. But I think this is a great place to ask our last and final question, which is, what is an idea that you had that you thought was a good idea at the time, but ended up being only good on paper?
That's hard for myself. I think, you have all kind of experiments that you do in the lab, and that's almost on a, weekly basis where you say, we should do this, we should do that. For example, in my first book that I wrote some years ago, Short History of Humanity, we speculated that horses, when they were domesticated, were responsible for the spread of plague. Now, that sounds crazy, but we had some reasons to think, because horses are partially immune to plague, that they played an important role, because at the point when horses got domesticated, the plague spread for the first time. And we thought that there's some sort of correlation here. And that might also explain why horses are more resistant to plague than other animals. At the end, what we actually could see with some of the data that was generated by some of our colleagues together with us was that horses were domesticated 1,000 years after the plague spread. So, okay, bada boom. So that that kind of like hypothesis is then kind of not substantiated. And that, of course, happens often in science, where you come up with a hypothesis and then you reject it. So that's quite normal. If I think about stories that kind of made me really excited over the last 20 years, kind of doing research, one thing that I was really hoping for is longevity and extension of longevity. There was much debate when I was, a student. The first human genome was deciphered, and now we can read it like a book, and we can switch off certain genes. We can extend the ends of the kind of chromosomes called telomeres that will help us to, become hundreds of years old. And being aware of mortality is one of the hardest things about being human. That kind of sucks. I kind of would wish to be a chimpanzee sometimes, and I wouldn't be aware of mortality as much as I am because I'm a human, because it sucks if, the lights turn off and that's it, right? It's gone, right? That was life, So longevity was something I was really excited about. But I haven't seen any progress in that direction over the last 20 years, despite the big revolution we had in genetics and in molecular biology. And so we don't really see that people get older and older, and we eventually still all gonna die. So that really, really sucks. So if you want to,
Well, hopefully someone one day is studying our genomes in the same way you're studying our ancestors. But Johannes, thank you so much for coming on the show. I really enjoyed talking with you.
It was really great to be on the show.
Good on Paper is produced by Rosie Hughes. It was edited by Dave Shaw and fact-checked by Enna Alvarado. Rob Smirsiak composed our theme music and engineered this episode. Claudine Abade is the executive producer of Atlantic Audio. Andrea Valdez is our managing editor. And hey, if you like what you're hearing, please leave us a rating and review on Apple Podcasts. I'm Jerusalem Demsis, and we'll see you next week.